All Seja. Right, awesome. So quick kind of overview of the primer series and what we are doing. So kind of we're trying to get the funding world more involved in machine learning techniques. And I think more broadly look at the idea of distilled human judgment, that we have humans already making judgments. How can we kind of create competitions where AIs are trying to replicate those human judgments? So one application to it is funding, which is what deep funding is, where people are a jury is voting and models are trying to give predictions of the weights. Another is predictive funding, where money is always a function of human judgments and models are trying to predict how much money a project will get. And the third is also things like community notes, where we see if a if a tweet got community noted, kind of was a model able to predict that a tweet would get community noted or not. So we're looking at these different kind of ways that we can apply machine learning to extend human judgments. And we've been holding a primer series for that purpose. And that primer series is to help all of the contestants build better models and to actually do it. So that's why it's like really important that we get experts. And last time we had a PhD student who taught about PhD models, about machine learning models. And today we have Rishi, a childhood friend, who is presenting on generalization in machine learnings and how to optimize it. So really cool, Rishi. You can take it away now. Yeah.
Sure. Can I share screen? I might need to send request.
Yeah.
Okay, do you see the title slide? And if I swipe, do you see me swiping? Okay, great. So thank you for the invite and the introduction. Hopefully I can build on some of the stuff you saw last time about generalization. As far as I can understand, this is supposed to be like a tutorial. So at any point, if you have questions, please stop me to ask questions and things like that. Also, we're supposed to have a vibe check to see how people are feeling. I decided to use some sheep. So if you could drop in the numbers for what your moods are like. I am particularly like 4 maybe today. So yeah. Okay. If everyone is good, maybe we can start talking a little bit about generalization. So the first thing I want to go over is this notion of supervised learning, just to like set up the context. So imagine you have some function that goes from X to Y that you're trying to learn. So examples could be maybe these are pictures, the 9 pictures we saw before. This is a little bit too thick. Anyway, so the 9 pictures we saw before, and maybe these are the numbers. And given a person, you want to predict which emotion they're feeling, right? So that is an example of like maybe a supervised learning task. And basically, in what's known as the empirical risk minimization framework, is you're given some data points. So you're given some inputs, some examples of people and their emotions. So maybe this is my emotion. So maybe this is me, and this was the 4. I don't quite remember what other people's was, but maybe you have Dewan with, I think he said an 8. Right, and so you have some examples, and now given like a completely new person, you want to predict their emotion. Okay, and you then have your parameterized family of functions. All this is your models. Different color. All right, so these are your models. Right, so you're trying to fit some model to your data, right? So okay, so that's the general sort of idea behind supervised learning. This is what you do in like most situations. And the classical goal of supervised learning is to solve this sort of problem. And so let me just break down the different pieces. So f hat is your model. So this f hat is the model. And you're somehow trying to minimize the difference between what you predict and the true value, right? So this is difference between prediction and true value. And then you just take the average over all your data points, right? So that's just some notion of how well your model is doing on your given data. And if we go back, I was using this like curly script f to be somehow the set of all models. So you just want to pick the model that minimizes, right? That minimizes this distance, right? So pick the one that has the best predictions. And then the idea was you want to understand this notion of generalization error, which is, well, not just how well you do on the data that you see, but how well you do on, say, a new data point, which is expressed in this format. And the idea is that somehow how well you do on the data you see is a good approximation for how well you do on the data that you do not see. Right? So this is the general sort of classical idea behind supervised learning. I would just want to briefly pause to see if anyone has any questions. No? Okay. So I think you saw this last time is basically you can take your generalization error and you can decompose it into two parts, which is this variance and bias. So basically, what are these two things? So if you imagine f hat or f bar is your expected model that you fit, right? So there's some randomness in your data. You can see what sort of the expected model that you learn is. Then the variance is the difference between the model you actually learn for the data you're given and the expected model. And the bias is the difference between the expected model and the true function that you're trying to learn. So what do these things sort of capture is if we somehow fix the number of data points we have and we change the complexity of our models, what do we think happens, right? So if we change how complex our models is, we might expect our variance to increase. Why is that? As well, because our models are more complex, they might be more sensitive to how the particular data we're given, right? So if our data changes slightly, maybe our model changes like a whole lot. So if we increase the complexity of the models that we're fitting, we expect the variance to go up, so it increases. On the other hand, if we think about the bias, as we increase the complexity of our models, then the true function we're trying to fit might be more likely to be in our space of models. And so our bias sort of decreases. And so I think you saw this last time, this idea of this bias variance trade-off, which is as the model complexity increases, your variance goes up, your bias comes down, and somehow how well your model does on unseen data is a sum of these two. And so you want to pick this middle ground where it does well. Right? And normally the way you pick this middle ground is by limiting how complex your models can be. And usually, or at least classically, right? So this is the classic. This is normally done by saying you cannot exactly fit your training data, right? So there will be some error in the model prediction versus your training data. But yeah, further questions?
Yep, we have two questions in the chat.
Okay.
Yeah.
Yeah.
Go ahead, David. Do you want to start? Yeah.
I think that's something that I'm quite curious about. As the model complexity grows, we should see the error increasing. In the current scheme of large language models, we see the error increasing like in the classical bias variance trade-off. But then we see the error decreasing again. And
Yes.
this double descent phenomena, does that align with classical bias
Right, so
variance
that is a great question, and is why I think the classical views are not correct. And so this is what I want to show with like an example, is this idea that you get this double descent, right? Like as you keep increasing model complexity, somehow this comes back down. And I want to talk a little bit about sort of like why that happens. Right, so this is exactly well predicted about what I wanted to talk about. So let's imagine we're trying to just fit a simple function, right? So imagine we're trying to fit this like oscillating function, and these points over here are our data points. And the way we're going to fit this is we're going to define a class of models that is mathematically written like this. But basically, you should think about each of these phi's as some function. And basically, our model is the sum of phi's, right? So it's something like, I don't know, 1 phi 1 plus 2 phi 2, and we pick some nice functions. Okay, right, so we pick some nice functions, phi 1, and I'm going to do this with some specific set of phi's. Here, these are polynomials. You can just think about phi I as being x to the I. This Legendre part is not too important, right? And so basically, we're trying to fit, like maybe if we are allowed to use only one function, then we can only use, say, x to the 0. If we're allowed to fit two of them, we can do something like x to the 0 plus x to the 1. If we're allowed three of them, we can do something like x to the 0 plus x to the 1 plus x squared, right? So as we're allowed more and more functions, we get more and more complex models. Okay, so what does classical wisdom say? It's like, well, if we start off with a few functions, we should have a large error between what we fitted and what we have, right? This is our bias is large, but our variance is small. As we increase k, right, the number of functions we have, we get to some local optimum, which is this idea that you've somehow found the correct balance between your bias and variance. And then if you increase k further, we can find some polynomial that exactly goes through all of these points, but it might have like very high variance or something, right? And then classically, at least in this setting, once we get to like 19 functions that we can add, then we can exactly fit our data and we're good, we're done. This is classically, we would stop here. We would only look between 1 and 19 and somehow find the thing in between. But as we were saying, we can consider k bigger than 20, and we can see what happens. Okay, so let's start with, yeah, question? No, okay. So let's start with, we can just fit, say, x to the 0. Well, if we can only fit a constant function, well, we get this line. It's a really bad fit, right? This is not what we want at all. If we're now allowed to fit something of the form constant plus x, so we now get a linear function, this is a better fit, right? We at least get this upward trend, but we do not get any of the oscillations whatsoever. All right, so we can go up. I can say maybe degree 5. So this is, I'm allowing you to fit something of the form x plus x squared plus x cubed plus x. Maybe let me not have it disappear. So C0 plus C1x plus C2x squared. Right, so I'm allowing you to fit something like this. And you can see it's starting to get some of these oscillations that showed up. Right, but it's still not a good fit. Okay, so classically, we would keep increasing. Here we get to 6. This is a slightly better fit. Here we get to 7. Now we're starting to actually go through some of the data points, but it's still not a good fit. We get to 14. And now we're going through most of the data points, actually, or very close to them. But now we're starting to get what you would have seen is this idea of overfitting, which is your variance is increasing, right? So you see these sort of like very big oscillations in the function. So I want you to keep an eye on the y-axis and see what the scale is. So the scale is on a log scale. So you can see this goes up to about 10, and this goes down to about 1,000, right? So it's quite a bad fit over here. So this is 14. Let's go up to 15. This got even worse, right? This goes down to a negative 10,000 and goes up to 100, right? So you're seeing quite wild oscillations. You can go up even further to 19. And so this is where the classical people would stop. And here you see like huge oscillations, right? This is 10 to the 5, which is 100,000, and you have like 10,000 down here. All right, so things oscillate quite wildly. And classically, this is where you would stop. You would not want to go further. You're saying, well, my variance is increasing too much. I need to backtrack. Okay, but modern, as you were talking about with LLMs, well, we just made the models bigger. Or in this case, I just added more functions. So I tried 20. And so if you were paying attention to the y-axis, right, this is 10 to the 5, this is negative 10 to the 4. If I went to 20, this is 10 to the 3 and negative 10 to the 2, right? So this shrunk by 2 orders of magnitude. All right, so our oscillations are already much smaller. So this is a better fit than we had at 19. What if we continue going up? This is at 25. Now you can see this is actually quite a good fit. We no longer have wild oscillations, and we still go through most of the data points. Right? If I keep going up further, this is 26. Things got even better. If I go up once more, 27, these are even better. And now you might start thinking, well, if I just keep increasing forever, I will get a better and better fit until like I exactly follow this curve. Unfortunately, that's not true. Here's 35. This still looks okay. Here's 45, and you're starting to see these oscillations again. And then this is 58. This is sort of the biggest model I could fit within a few seconds on my computer. And you already see you have these oscillations again. Okay, so does anyone have questions about what we just saw?
How's that explainable in terms of bias variance trade-off?
Okay, yes. So that's exactly sort of what we want to do over here. So if we plot our test error, right? So this is the degree of the polynomial we could fit, and our test error, we see we get this sort of like up, down, double descent sort of phenomenon. And so what is where is this peak, right? So we really don't want this peak, right? We want to avoid it. This peak is exactly at this point known as the interpolation point, which is when your training error is 0, right? So this is when you can exactly fit all your training data points. This is the first time your model is like complex enough that you can exactly fit all the training data points. And the issue, right, the reason, let me draw the error curve, right? So the error curve looked like this. Oops, that's the disappearing one. And if I draw the error curve looked like this. So the issue was this assumption that the variance is monotonic, right? So the variance is actually not a monotonic function in the model complexity. It actually turned out the variance comes back down. So why did that happen? It's because of what's known as the inductive bias of a learning algorithm. So when we have let's say 20 data points, let me write it again. Let's say you have 20 data points, but your model has like 100 parameters, right? So this is a lot more parameters than model data points, Then you have many models, right? So not just one, you have many models, right? So the whole space of models, which have 0 error on the training data set. So now, since you have many models that have 0 error on the training data set, your learning algorithm somehow has to pick one, right? Like it has to pick one of these models, right? When you train a model, it can't give you all of them. So it needs to pick one. And which model it picks is known as the inductive bias of the learning algorithm. And what it turns out, at least in machine learning, is that our learning algorithms have good inductive bias. right? And so from this space of many models that you could pick from, they tend to pick a model that actually has lower variance than before. And this is why sort of your variance goes up and then comes back down, and you can fit things well. Okay, so that's sort of the
I have one other question,
Yeah.
which is about
Yeah.
the variance bias trade-off. So with
Mhm.
variance, I can see why it's an issue in terms of like getting spikes, which are predicting something completely off. But where
Mhm.
does bias show up in the example charts that you had showed?
Okay, so this is, let me go all the way back. So this is a model with high bias. There is a big difference between the model you learned and sort of your training data and the actual function. So this is not the usual word bias, right? This is somehow a different usage of the word bias. But this is basically saying that the model class you have is like not complex enough to model what you want. So there's a big difference between what you can learn, which is this line, and the true function.
Right. And in general, is it worse for a model to have high variance or worse for it to have high bias?
So in general, it is worse for it to have high variance. So the variance is the one that really drives up the error. Normally models, once you have like enough parameters, they tend to have low bias. Does that answer? Okay, great. So then, right, so this is this idea of the modern regime is right. So previously you would imagine your test error goes up and down, and your training error, as you increase the model complexity, just keeps going down. But there is this point known as the interpolation threshold, which is when your model is complex enough, you get to this point where you have no training error, right? So you fit your training data exactly. At this point, actually, your variance is maximum. So here is when variance is maximum. And then as you keep increasing your complexity, your inductive bias gives you nice models that have low variance. And so this error comes all the way back down. Okay, so this was one example where we were fitting sort of like, where we were fitting some model to our polynomial data. And we saw this thing that having increasing model complexity can be good, or initially is good, then it's bad, and then it's good again. Okay, but I want to say this double descent is not only related to model complexity, it can be related to something else. Okay, so let's try another problem. So this is, just think about denoising images. So imagine you have some data set of noisy images, and let theta test be the signal level of the test data set, right? So what this means, so if this number is high, that means there's very little noise. If this number is low, that means you have quite a lot of noise, right? And now you want to train some model that takes in a noisy image and removes the noise. So to train this model, you have some clean images, right? So you have some images that don't have any noise, but to train it, you need to artificially add noise. So one question I'm asking is, how much noise do you need to add? Does anyone sort of have a guess? Also, I see a question in the chat, how to know whether our model that has low error loss is overfit or tends to have good generalization. So that is hard question in general. I would say you should split your training data into a training and validation test, and then you just need to check whether the validation error is similar to your training error. Sample from a normal distribution. Well, that's how you could get the noise. I'm asking how much noise there is. So like maybe, for example, I don't have an example, but maybe I want to draw like a image of a house, right? And maybe this thing has, I give it some amount of noise, not too much noise, maybe this is some amount of noise. And then I have another image of a house. Oops. Right, and this one I add a lot of noise. Right, and so maybe this corresponds to like a theta of 1, and this corresponds to like a theta of 10. Right? Okay, so it's unclear, sort of. I see a whole bunch of different answers for how much noise should be added. And the answer is it actually depends on the amount of training data you have. Right, so I'm going to run an experiment. So this is an experiment with real data. So it takes images from this thing called MNIST. This one is MNIST. So these are digits, images of digits. So they're like 0, 1, and so on. So I'm going to imagine that my test data has a signal that's over here. This is a theta of 0.1. So this means this is like 90% noise. Right? And so the question is, well, how much noise should I add? So I trained the model. So on the y-axis over here, you see how well it does on actually denoising my data set. And on the x-axis is sort of how much signal I saw, how much of the image I saw. And so it says that when I have 20 data points, I actually do best when my noise, when I saw maybe this is like 35%, right? So I saw 35% of the image and 65% was noise. So, but the important part is that this is to the right of the test, right? So this is where test is. And so basically you wanted to see cleaner images. Well, so you want to train a model, right? So your model, the thing you're trying to test on is removing noise from some data. Okay. Wait, does that answer the question? I don't know what the thumbs up means, or is that someone else?
Yeah, that's someone else giving the thumbs up. And I guess the question is that in the training data, why would you want to add noise if you're not telling the model that this is noise?
Okay, so let me maybe go back to so you have some data that is noisy, that exists somewhere, that is given to you by someone, and you have some data that is not noisy, right? So you have both. So you have some noisy data and you have some clean data. And the task you want to do, the task is remove noise from noisy data. Right? And so the way you do this is you can train a model that takes in a noisy data, and you need to tell it what the correct answer is. Right? So to set up that thing where it takes in noisy and outputs not noisy, you need to take your clean images and add noise to it. Did that help?
That's actually pretty useful. So it's kind of similar, I guess, to weekly supervised machine learning contests, where you have
Yes,
like
this is like a this is like a self-supervised or weekly supervised problem. Yes. Right. And so the question is sort of like, how is the noise level on what you want to do compared to like the amount of training data you have? And I'm saying, well, if you have very few training data, maybe you want to see very clean images. But okay, let me increase the amount of training data. I go to 200. And now the best performance actually happened at noisier images, right? So if I have more training data, I can have noisier things and still do well. If I keep increasing my amount of training data, this is actually at 0. So the best performance happens when I have 0 signal. So this is when theta equals 0. So this is saying I should be training on pure noise. If you understand that, that makes absolutely no sense, right? This is saying your model should be trained on nothing but noise. And somehow that is when you do best, when I have this amount of training data. Let's say I increase my training data even more to say 1,000. This is still, it wants you to train on basically noise. Let's go up further to 5,000. And okay, now you can see it wants you to train on like something that is not just noise. And if you go up even further to like 20,000, then you can see the amount of noise it wants in your training should be about the same as you see in the test. Okay, this makes a lot more sense, right? So when you have a large amount of data, you want your training data to be similar to your test data. But there is this weird regime that when you have a fixed number of training data points, that is, say, 700 here, you want to train on complete noise, right? And so what happened here? So if you plot our generalization error, so I'm going to plot it over here. So this is how well you did, your test error, versus the amount of training data points you have. You see a double descent again. Right? And if you plot your test error, you can see it goes up and then it comes down. And again, if you've trained any models or even think about this for 1 second, this makes absolutely no sense, right? Somehow, if you have more data points, you do worse, right? So there's a regime where more data equals worse performance. And this is not just something you see sort of like in this one example that I've shown. There's this paper by Pritam Nakiran and people from Harvard. It's titled when does bigger models and more data hurt? So there's this thing where adding more data can make your model do worse. Okay, so I want to stop at this point to see if there are any questions.
That doesn't make any sense.
Yeah, that makes absolutely no sense, right? But this is unfortunately what we can see in practice and we can prove theoretically. Oh, here's another example where I do it with a deeper network, but you see the same thing. So maybe let me try to add a page to talk a little bit about this. Okay, so just to see what we saw, we've seen if you have model complexity, you see this double descent. If you have data, the amount of data, you also see this double descent. So what is actually happening is you somehow really care about complexity over the amount of data you have, right? And let's say maybe you want to think about complexity as sort of the number of parameters in your model, right? And so you can think about this ratio between so complexity is not the amount of data, right? Complexity is the number of parameters in your model, right? Let's say maybe you're allowed to learn like 3 parameters or 4 parameters or 15 parameters. And what these two things are saying is you do not want this ratio to be close to 1. Right? So if this ratio is close to 1, things are bad. Right? So if this ratio is close to 1, that means you're sort of in this regime over here. And things do not work. And we saw this sort of via 2 examples. One is you either increase the amount of data, right? So maybe this ratio starts at some big number, and then you increase the amount of data until you get to 1, you'll get this double descent. Or maybe this ratio starts at like a small number and you increase the complexity until it gets to about 1, and you see bad things, right? So basically you don't want it to be around 1. And in practice, either extreme on the other side here or here is fine, right? So you can get, so if you either send this ratio to 0 or to infinity, either one of those things are good. Question, is there triple descent? Yes, there's triple descent. There's also quadruple descent. There's also quintuple descent. You can actually have as many descents as you want. But those are sort of quite artificial. Those are not things you see in practice. Those are things where I can like construct this weird made up problem and this weird made up model, and I can show it has these multiple descents.
I think another question that you missed from David is, are neural scaling laws wrong?
So no, neural scaling laws are not wrong, right? So the whole point of neural scaling laws is to figure out how to, what is the appropriate ratio for this thing, right? That's basically what the neural scaling law is trying to tell you. Right, and I'm telling you right now, at least, we know we should avoid one, and we can prove this sort of theoretically and see it empirically. The neural scaling laws are sort of more empirical. They try a bunch and try to figure out what this ratio should look like. They have some sort of thing where this should look something like n to the negative alpha, where n is the amount of data points. That is a good ratio. This is this chinchilla paper, if you want to look it up. Okay. But related to the questions you had, I also have a whole bunch of questions about this. Question sort of one is, when does this occur? Does it always occur? Does it never occur? Can I predict when it occurs? When it does occur, can I tell you where the peak is? Right? I don't want to be anywhere near this peak. I want to be far away from it. Once I have this peak, right? Let's say, oops, get rid of this. I have this peak. What happens to the right of the peak? Does it continue going down? Does it potentially go back up? We saw two examples. In the first one, it went back up. Second one, it stayed down. Let's say even if it does stay down, where is the minimum error? Maybe it's smaller over here than here. We don't know. And the final question that I care about the most is, how do we mitigate this? Because it makes no sense, right? It does not make sense where you increase the amount of data to decrease, to get more error. Okay, so this is the last part. This is mostly quick. So when does double descent occur? It occurs due to mismatch. If there is any mismatch between the model you're fitting and the data you have, you will see double descent. So unfortunately, this is not something we can avoid because you don't know where your data is coming from. So you fit some model to it. So there will always be some mismatch. So unfortunately, this is not something you can avoid. Where's the peak? So I said, well, the peak is normally when the number of parameters in your model is equal to the number of training data points. This is usually true, but it can be false. Not every data point is equal. Is it really the data cardinality or a certain category of data that creates the peak? So this is, I'm going to say, this is a third prediction, even though I'm not going to talk about it. That's exactly correct. Not all data is equal, and we can talk a little bit more about this if you want, sort of offline. I don't have the slides for it here. But in general, if you think about all data as being equal, then these things should be similar. Okay. So when is the best error? Is it to the left of the peak, to the right of the peak? Well, this question's a lot harder to answer. Most people believe it's to the right. So this is where you make models really big. And this is where these scaling laws come from. So it's just trying to figure out how big this model should be. Though in many cases, actually, both sides do equally well. So you can imagine you have infinite amount of data compared to how complex your model is. That model should do quite well. But on the other hand, if you have very few data, somehow you want to make your model extremely complex. Yes, you should be making the number of parameters much bigger than the amount of data you have. This is what happens sort of like in these models, right? This is why you talk about the 70 billion, the 700 billion, the 7 trillion model, right? The data didn't change, right? They just made these LLMs bigger. And in particular, it's difficult to count, but over there, they have more parameters than they have data points. Okay. So now, can we avoid having a peak? Yes, the usual way you avoid having a peak is to do this thing called regularization. There are different types of regularization. Here in this graph, I'm sort of like just plotting how much you regularize. And you can see sort of if you have no regularization, you have the peak, but you get to this regularization, you get this nice curve that just is monotonic. So regularize your models. Here's another example. This is with like actual images and data. Again, depending on how much you regularize, you get this nice decreasing thing without having a peak. Okay, the different types of regularizations. One is you can add noise to the problem. This is like your weakly supervised or semi-supervised or self-supervised things. You can add a weight penalty. If you're familiar with regression, this is like a ridge penalty. I think the speaker last time spoke about early stopping, which is where you train a model and then you stop it early. All of these are types of regularization. And if you do all of them correctly, they all prevent double descent. Well, if you do any of them correctly, they all prevent double descent. So that's nice. One idea, this is sort of an aside that I'm going to just throw out there. Another way to avoid double descent rather than, right, so regularization, this is reduces model complexity. The other way to avoid double descent is to increase the amount of data. And I claim you can increase the amount of data using this data augmentation. And you can do data augmentation, I claim, in a lot of different ways, and it works. One way you can do data augmentation is just take the data you have, add new noise to it, and now you've doubled your data set. Now you can take it again and just add new noise to it, and now you've like tripled your data set. And this works very well in increasing the amount of data you have. And this moves where you are in this complexity versus data space. Another way you can do data augmentation is just take different data for a different problem and just add it to your data set. And this also works surprisingly well in practice. Just to give you an example, so here, these are images from different data sets. So CFAR is like images of cats, dogs, planes, etc. SDL10 is similar. SVHN is, again, things of digits. So here, I just added new noise to increase the amount of data. And you can see you sort of get this double descent where I move on the x-axis based on the amount of data I have. I can also do it by mixing data, where I mix these data sets. And even though they have completely different types of images, you can still move sort of to the right on this x-axis. Yes, you can add bad data, and it's fine. So for example, over here, these CFAR, like I said, is images of cats, dogs, planes, and I added to it images of zeros and ones. And just adding to it images of zeros and ones was good enough to increase the amount of data and reduce my error. Blank images are not quite good enough, right? So you can add pure noise images or like highly noisy images. So I would suggest rather than blank ones, I would just take the ones you have and just add some noise to it to create a new copy. Right, and this is this idea from this paper called SimClear. I don't know if you want to look it up, which is just take your data, and let's say I have images. I have another one where the images are slightly rotated or slightly shifted or slightly more blurry. And this does quite well. This is a paper by Google in this image classification. Okay, so that was sort of most of my presentation, which is, I'm going to skip this. This is quite a cool thing, but it's sort of an aside. Which is basically this conclusion. We see this bias variance trade-off need not be true. We see this phenomena called double descent. How do we fix double descent? No, data pruning can also be good, right? It's really, it's quite hard to say exactly what happens when you remove data compared to like where you are on the curve, right? Let's say you're here and you're here on the curve, right? So this is your model is much more complex than the amount of data you have. Now, if you remove bad data, this moves you further this way. So you can increase performance. But if you're here and you remove bad data, it moves you further this way. And that could actually decrease performance. So you have to be very careful about where you are on the curve. But yeah, so in case of GANs, you can do this. So my go-to approach is to just take your data and create a new copy of the data with some noise, and then create a new copy where you get some more new noise. And now you have like 3 copies of your data. I would suggest this. I think this is a very good. So what you do to regularize is sort of like you train your model for less amount of time. You can regularize by increasing the amount of noise you add to these things. Both of those are sort of good approaches, right? And then this final thing about scaling laws, figuring out how these 3 things relate to each other, is this very active area of research called scaling laws. Okay, and I can talk more about regularization if you have like specific models, but the idea of regularize is to just reduce the amount of computational power you give your model. Okay, so that was what I had. Thank you. And are there more questions? I might stop sharing my screen.
Hello, thank you for the
Hello.
presentation. Yeah, I do have a question,
Yes.
kind of related, but not exactly. I was curious if there is a way to do a text regression, like instead of having different features, you just feed in the description of the things that you have, and then you assign them a label, like a numeric label, and then you want to do like regression just based on this text description that you have. Like, I was wondering if it's just possible or not.
Sorry, so let me make sure I understand. So you have some text and you want to predict labels for each bit of the text.
Yeah, so each text, for example, is describing a house, and then as the label, I have the price of the house. And now instead of like breaking down the house into like different features that it may have in a structured way, I just have this human readable description of the house. And also like in my training data, I also have the label. But then now I want to be able to predict the prices given the description of the house, like without
Yeah.
ever having the structured like data either in training or in like when you're querying the model.
Yeah, so you could train a transformer. So transformer or one of the language models that takes in text and you wanted to output a price. I don't know if that was your.
So yeah, a follow-up maybe. Yeah, that was helpful. Like how big can these descriptions be? Like
So that is a great question. So it really depends on how much computational resources you have. So like if you have a lot of computational resources, you can make these descriptions sort of really big. They could be like pages and pages and pages of descriptions. But if you have a limited amount of computational resources, then you might want to restrict how big these descriptions are.
Interesting. And also, is it possible to use like LLMs to do text regression, or like LLMs cannot fundamentally do these things well?
LLMs can do regression. This has been
Interesting.
proven. So actually what you can do is LLMs can do regression in context. And so this is what it means to be in context, is you basically give it in the description a bunch of examples of descriptions and price, descriptions and price, descriptions and price. And then you give it a new description, and it can do the regression task. And so people have shown that LLMs can do this sort of in context.
So,
You
but
don't need to
isn't
train a model or anything.
And isn't the limitation in the context of an LLM, wouldn't that limit the amount of like examples that you can give it?
Yes, it limits the amount of example you can give it to like how big the context is. I don't know how big a context most LLMs allow you. Maybe DeepSeek, the new one from China, will allow you to have a whole bunch of context because they're
Right.
supposedly 1/10 or 1/20th the cost, so they could probably do bigger things. Does double descent also happen in context? Well, the double descent is more a phenomenon of the problem and not the learning algorithm necessarily. Well, it's also part of the learning algorithm. I actually don't know. Sorry for that, David. I actually don't know if double descent can also happen in context, but I think it does. Where sort of like if you give it too many examples, it can start doing badly. But I think the issue is if you then want to increase it further, then this context becomes too big, and then it does badly for other reasons. Actually, maybe I'm going to change my answer. Maybe it doesn't happen in context.
But it could be like an O1 model that reflects about itself.
It could, yeah.
Yeah. Interesting.
Um,
I had another question on the metrics. Do you have a kind of a measure or a rule of thumb what data I can add or what data I cannot add? You mentioned blank images are bad, but pure noise is okay. Is that objectively measurable, or is that something that I can only find out empirically?
That's sort of mostly empirically. I would rather really not add either blank or pure noise. Like I said, my go-to would be to somehow take your data and corrupt it a little bit. Right. So if for the example of text to price prediction, I would take my description and just randomly change some words. That is now a corrupted description, and that's now like a new data point. Okay. All right, I guess no more questions.
Yeah, no more questions. You guys were the ones.
Yeah, this is definitely one of the meteor talks that we saw.
All right.
And
Hopefully helps train models.
yeah, all right. Yes, thanks a lot for doing this and doing it. And I think all of us just have a lot to process. I got all of it, which is actually the good news. So you were good at explaining it to to a beginner as well. And
That is good.
yeah, and yeah, we'll definitely be sharing the video with a lot of people who are submitting and take part in our contest. So thanks for that and jumping on.
Yeah. For sure. Yes, regularize your models. They're good things to do. Okay.